So this time, let's spend a little bit of time going through a graph that's a little bit more unusual. We've got 3 times x to the 2/3 minus 2x, and we want to, again, analyze and sketch this graph of the function, label any intercepts, relative extrema, or points of inflection, and asymptotes if applicable. In this case, actually, there are no asymptotes. And the reason why is that this function is actually defined for all real numbers. We've got a root, right? We can think of this as a cube root of x squared. The cube root is defined for all real numbers. And so right away, we can actually identify our domain, which is one of the first things we should always do here. Identify our domain, and in this case, that's all real numbers. As far as the range goes, I'm not sure yet, but it doesn't seem like we will have a limit on the range, but we'll have to see. If we have a maximum or minimum, we might find that that is the case. So let's see what's going to happen right here. I believe it's a set of all real numbers in this case. How about x and y intercepts? Well, of course, x and y intercepts are found by setting the function equal to 0 for an x-intercept. So we set f of x equal to 0. See what happens if we take 3 times x to the 2/3 power minus 2x and set that equal to 0. We need to find a common factor. Well, this is x to the first. 2/3 is less than x. So we can factor out x to the 2/3. Well, we say x to the 2/3 times what gives us 3 times x to the 2/3. That's just 3. We say x to the 2/3 times what will give us negative 2x? Well, the answer has to be x to the 1/3. Why? Well, yeah, we have to add our exponents. 2/3 plus 1/3 gives us 1. And so now we're going to have this equation where zeros will occur wherever x equals 2/3 is equal to 0, and that's simply x equals 0. And then another point where 3 minus 2 times x to the 1/3 is equal to 0. That's a fractional equation, but that's not too bad, right? Because we come out with something like 3/2 equals x to the 1/3 power. And to get rid of a 1/3 power, we raise everything to the third, so we actually get a value that looks like x equals 3 to the third, 27, over 2 to the third, 8ths. 27/8. 27/8 is approximately, if you're looking for a decimal number, well, approximately, it goes into 27 3 times 0.375. So that's our decimal version of that. If you want to have a sort of a beat on where that's going to go on your graph, it helps to get that decimal value. Okay, so we got x equals 0 and x equals 27/8. Those are our two intercepts, 0 0, which is also our y-intercept, and 27/8, 0. Okay, not too bad. Next, we need to find our derivative, f prime of x in this case. We use our power rule for both terms. We say 3 times x to the 2/3 becomes 3 times 2/3 x to the negative 1/3. I'll work this out for you. 3 times 2/3 x to the negative 1/3. 2/3 minus 1 would be negative 1/3. Minus 2 times 1, and simplifying that down a little bit, we actually have this expression 2 divided by x to the 1/3 power. Minus 2 is our derivative. Well, if we're looking for critical numbers, we're looking for any points where the derivative is either undefined or equal to 0. We already have a place where f prime is undefined. It's undefined at x equals 0. You can see why, right? 2 divided by 0 to the 1/3 is undefined. It doesn't matter that we're subtracting 2. Of course, we also have to set f prime equal to 0 and find out if there's any solutions to that. And we've got this equation where 2 divided by x to the 1/3 power is equal to 2. And so we're going to have to solve for x. A little bit of algebra proves that we get x to the 1/3 is equal to 1, right? Multiply both sides by x to the 1/3 divided by 2. You get x equals 1/3. That gives us the value x equals 1. Well, that's convenient because that means that f of 1 is our another critical point. So we have two critical points right here, 0 and 1. And on our number line, we'll want to figure out, well, what does that mean for the value of our derivative? Is it positive or negative? So here's 0, here's 1. F prime of x, we want to determine whether or not this is positive or negative to find the intervals of increasing and decreasing. So we're going to use this derivative to find that and test f prime for numbers, let's say, that are less than 0. Let's try negative 1. What would happen at negative 1? Well, negative 1 to the 1/3 is negative 1. So we're taking 2 over negative 1 minus 2. That's a negative, folks. Let's try 1/2. 1/2, let's see, 1/2 to the 1/3, whatever it is. 1/2 to the 1/3, and that's 2 divided by that minus 2. Now, if you work that out, and you're very careful, you're going to find that's actually a positive number. That's a positive number. So we have negative, positive, then we try a number greater than 1. Let's test 2. What's going to happen there? Well, that would be 2 over 2 to the 1/3 minus 2. And if you work that out carefully again, get a decimal, you'll see that you get a negative number there. So in fact, we have two intervals where we're decreasing, one interval where we're increasing. So it's a function that is going to have a critical number at 0, 0. We have our undefined derivative point, and at 27/8. I'm sorry, not 27/8, 1, 1, right? 1, 1 is our critical number. 27/8 is our intercept, right? 1, 1, 1, 1. And it looks as though we've got a maximum point right here, a relative maximum point in any case, and it's going to start decreasing again, probably towards negative infinity, so there is no minimum. And we're going to have a relative minimum here at 0, 0. So we've got our minimum, we've got our maximum, we've got our intervals of decreasing and increasing. Let's take a look at the second derivative. The second derivative, in this case, if we work that out, is going to be, let's try that out. We're going to be taking the derivative of 2 times x to the negative 1/3 minus 2. Well, that constant goes away. And we're actually left with an expression that looks like this. Negative 2 divided by 3x to the 4/3. Now I leave it to you to again verify that this is the case. You may want to pause the video and check this out with me. We have only one critical number for our second derivative, and that's at x equals 0, where the second derivative is undefined. But the second derivative is undefined at the point where the first derivative is undefined. What that means for us, well, we'll have to see. But let's check it out. If we check out 0, and we choose a number to the left of 0, let's say negative 1, negative 1 to the 4/3 becomes positive 1, and negative 2 over 3 makes that negative. Then we try, let's say, positive 1, where we had our maximum. And if we check out our maximum there, positive 1 to the 4/3 is 1, so we've got negative 2 over 3. It's negative again. So this function is concave down everywhere, and there are no points of inflection. No inflection points, all concave down. So, of course, our range now, that makes it all real numbers. Let's take a look and see what that means to us here. Okay, so we have this function that has our x-intercepts at 0, 0, and at 27/8. That's 3.375, slightly more than 3 1/3 right there. We have a maximum. We said a maximum at 1, 1, a relative maximum. What's more, we said that this function was going to be decreasing on the interval from negative infinity to 0. It's going to be increasing on this small interval between 0 and 1. And it's going to be decreasing again on this interval from 1 off to infinity. So decreasing again. Now, of course, we also said that the function was concave down for all real numbers except at 0 where it's undefined. So it's concave down on both of these intervals. So what would that look like? Well, we're going to have this function that to the left of 0 is decreasing and concave down. If I'm drawing that, that's sort of this steep decline, but that would be curving slightly downward. You can imagine it like this if you want to, but curving slightly downward. And if I were to look at the rest of the function, what should happen here is that this function should be increasing up to our relative maximum. There it is at 1, 1, and then decreasing and passing through the x-axis and going towards negative infinity. So there it is. This is sort of a picture of our graph of f of x equals 3x to the 2/3 minus 2x.